I think everything is working. I struggled a lot with the setup last week. Basically, everything I tried in the code was working first time, but everything related to the stream production was failing. It was super frustrating. I hope it will go better this week. I'm also back on a Monday, which is actually the plan. My plan is to stream on Monday and to. So now I have some sound return. I think it's my phone, which means the sound is working. Okay, that's a great start. Anyway, let's go back to what I know to do, which is code. So last week and the week before, we started working on something I call the activation virtual machine. A bit of context again. So there are some there is some notes here which are relatively easy to find by going to github.com/sonos/tract and looking for the issue 1008. And basically, so the idea is that in a neural network you have these activation functions, which are essentially functions that are executed on every single value of a tensor. And so your output tensor is the result of applying the same function on every input value of the input tensor. And they are used usually after a big linear algebra operation. So you will do a big matrix multiplication and then you will apply some kind of activation function. And you build your neural network model by stacking alternatively linear operation and activation function. Or, I mean, that's more or less the idea. And so we look into the ONIX specification for various kind of activation function. And so some of them are very easy in that they're made of very simple operation like comparison to 0 with an if, some multiplication, some are even simpler where you take if x is over a number, you take x. If it's below, you take 0. And some are a bit more complicated, like this one. But then some are super complicated. Like the worst we found was this one, Mish. For now, I more or less decided that I didn't want to know about that one. I mean, it's already, it would be pretty easy to handle in Tract anyway, but I don't want to spend too much time optimizing it because I think it's so complicated to compute that basically you should look into alternatives if you're trying I think that if you're trying to get what Mish is doing, you can probably obtain the same thing with a hard switch or some other function, so it's not that relevant for us. I mean, I don't want to spend too much time optimizing these, but the good thing is we found a way to we found a minimum assembly language that could handle all of these. That was in the first week, and we implement the first version of it. And on week 2, it was a bit bumpy because I mean half of the stream is missing because of all the technical difficulties that I had with the production. But we find a way to compute rational approximation. And the good thing with rational approximation is that there's the right thing that you want to use to approximate this family of functions, which are super important. I mean, hyperbolic tangent and sigmoid are all over the place in neural nets. So we really want these two to be relatively optimum, and the way to do that is to go through rational approximation. So by adding a couple more of operation to our VM definition, we managed to compute also these guys. And one thing that I didn't expect, we also managed to make a function for the exponential function. So if we have a look now at our operators, I'm in the right place, maybe not. I'm in the right place, but not in the right branch. Activation, yes. So activations, here we go. So these are the operators that we need to implement our VM. So we have some operation to move stuff from one register to another, or to load a constant into a register. We also have this one which will switch the register B and the register C. It was interesting because at some point we did have to swap, and we did it through the D register, and as it turned out, we don't need the D register for most, I mean, if not all of the functions that we have implemented. And so here we have all the activation functions that we managed to port to this new small language. So ReLU is super simple, but we have affine, Nikki ReLU, threshold, soft sign, etc., etc. And then we have this, the two big ones, which are so I only did sigmoid, I didn't do a tangent hyperbolic, but it's the same, exactly the same structure, so there is no, I don't think there is any difficulty. And all of these we managed to do without using the D register. We have exponentiation here, or at least exponentiation in base 2, but going from exponentiation in base 2 to regular exponentiation is just a matter of doing a multiplication. So it's super interesting to have this one. I mean, at least as a proof of concept. And we did some tests using prop test and using our reference implementation of sigmoid and the reference implementation of exp2, which I stole from faster math, a library, relatively common, code is on GitHub. Okay, there's a bit of cleanup here. So next stage, I want to bench the reference implementation. I want to bench the reference implementation and the VM implementation for these functions. And first we will just use the current non-vectorial implementation of the activation VM. But once we have done that, we could start looking into actually making it vectorial and compute several values at the same time. So let's do this. Is this limit to the right place? Not really. More? Yes, more. Here we go. May have an issue with the bottom of my screen. Yes, this is what. Okay, so one more OBS difficulty. My screen capture is on the right size, so let me fix that very quickly. Okay. Here we go again. No, it's still broken. Oh, come on. Why is it not? Yeah, that's the one I want to change. Sorry, won't take long, hopefully. And hopefully you will see my entire screen, or at least the part that I want to show. Yes, here we go. Now we're there. Up. That's better. Okay, no, so all fixed. So I said I want to bench. So to bench, usually I use a library called Criterion. So let's add it to our project first. And I guess, yes, it went to the dependency, and I want to make it only a development dependency, because I don't want to ship it, just to run a bench. Then we need, so we will do a benches directory. And we are going to start a bench. So let's call it VM. And to bench with Criterion, there is a bit of ceremony to set it up. So we need yeah, wrong site. Here we go. So let's go to the user guide. We'll grab some examples, hopefully. So, yes, I need to do this. So let's declare our bench, and we'll call it VM. We need this because Rust has already something built in for what? Cargo check. Rust and Cargo already have something built in for benches, and we need to say to Rust that, to Cargo, that we will not be using it. So that's the harness. So the harness is basically template main function that Rust will just inject into our code to make the bench work, but we will need to use the harness from Criterion instead. So the harness is provided by these two macros. I think I need to grow the font a bit. Yep. And here we go. So I'm done with this one, and I'm just gonna cut and paste the example and start from here. Okay. Cargo bench. So there are two variables, or three variables in what we are trying to bench. The first variable is, are we using the reference implementation of the activation function, or are we using the new one, the one we are trying to define with the VM? The second variable is, which activation function are we considering? We have like a small dozen of them. There are these functions. And finally, the last and probably the most important it's super important, the number of values that we are going to compute at the same time. If we are going to compute just one value, the reference implementation will probably be the best in all cases. I'm expecting the VM to be slower than the reference implementation in most of the cases. But once we have done this bench, we are going to do another VM that, instead of computing one value at a time, will compute them by several at a time. And we'll see how we can implement that. Okay, so this test doesn't help me a lot, so I think I need to expose my reference implementation of each function so that I can call it. So for instance, here when I did the test, for each and every function I did reference implementation. So it's super simple for Relu, and then it gets more complicated. If I want to compare, I need them as function. And I already have used the short names here, so I'm going to move. Nope, they're in definitions, so that's good because it means I can do a second module called reference, and I will move all of the function, all of the reference implementation in this module. Starting with, I'm gonna just cut all of this reference. Here we go. So these are not tests. Okay, a bit of manual work here, but it's okay. And so I need to make this function of x. I will get rid of test prefix. I will remove in any f32, and I will replace this with function of f32. Do it again and again. Then can I do something smart? Not sure. So yeah, going to do something dumb. Here we go. Up. Up. That one, I already have the function. Up. And the last one, that's, so here we have two reference implementation. One comes from oh yeah, this is the one from the one I stole from faster math library. So that's fine. I'm gonna put this reference implementation here. So the problem with all of these functions is that they return f32, and I need to fix the return value. So let's try this. 32. Okay, then okay, a bit too many, but now Yeah, one more and one more. Okay, I will make them pub because I want to be able to call them from about anywhere. Okay. This module will be made public so that I can call it from the bench. And okay, so here, sorry for each test now. I should probably make a macro because really what I want to do is super reference relu of x and there's a bunch of them. Reference that's affine of x alpha beta. Fix it, please. Will you fix it? Why? Why? Okay, probably because there's a problem later on. So, okay, this will be super reference leaky of x and alpha. Yep, that's it. This is super reference threshold ReLU of x and alpha. Fascinating. Reference subsign of x. Super reference switch of x. Yep. 3 more. Super reference sigmoid of x. Super reference x to f of x. So this one, yeah, I wanted to test. So I'm gonna delete this one because I know that this code is working now. It was just translation from the C code, so there was no really any suspense. And finally, I can compare with super reference okay, it's better. So why is it broken? Why is the formatting broken? Def one too many. Close enough. No, that's just right actually. Subsign close enough. Prop. Yep. So what's wrong? Let's just try to comment all of these and we'll put them back one after the other. Okay. Let's So this one doesn't want to auto format. Why? Super reference hard switch of X. Let's see what the compiler has to say. What the compiler has to say. Okay. The compiler is happy, so it's only the formatter which has a problem with this. Yes, so I'm gonna shift them to the right place by hand. I'm gonna assume the formatter is broken and okay. So now what I'm going to do is I'm going to sigmoid is not working. That's my bench. I'll come back to that. src. I'm going to convert the main into a library because as I need to call the function from the bench, I need them to be in a library and not in a main. Here we go. Okay. Trying again the auto formatting and it's still broken. Okay. What if I do it from there? Still broken. It's true, I'm actually in the prop test, yeah. I think that's the reason. So prop test is a macro, so the formatter in a macro is a bit weird. So now I will make definition. I will make this module public because I want to be using it in my bench, and same for reference, but that's already done. Something is not good with the sigmoid. Is it random or is it all the time? Okay, well, we'll debug sigmoid. So this is the standard implementation, that's the implementation in scalar mode in tract. And so we're calling it with x equals -14. And we don't get any result. We don't see the result. So let's try and see. So just putting back the debug that was there. And I'm going to put some debug in the main loop of the interpreter. So that would be here. Yes. Okay. So sigmoid. So we should find 1/q. So yeah, coming back from the end, we're adding const 14, which is half. So here we have -half. Here we have basically nothing. And we okay, I'm a bit lost. I want to see the operator at the same time. Okay, I just want to check that I didn't make a stupid mistake. So this is sigmoid, reference sigmoid calls S sigmoid, so it's okay. And we're running at -14, so we should find, in the negative we should find 0, and we find something close to 0, so it looks fine actually. Let me check what these two guys are saying. So this one, and because I can see them here, they're not shown by the macro from prop test. Yes, I didn't put it in the right place. It goes inside the close enough. Yeah, and the reason is we're calling close enough. And close enough doesn't show we will debug A and B. We'll need this quite often, so if not result, I'm going to debug A and B and return result. So I can remove my debug calls here. So yeah, I mean that's close enough actually. That's pretty close. And so what is the reason why? Because I just cut and paste something that was on. I mean, I think it was a definition from the Python, from NumPy or something like that. So we're doing the difference, and we're comparing the difference to max of arctol, so that's relative tolerance of max of absolute value of both plus atol. Atol is pretty low. Okay, I don't want to spend too much time on this, so I'm gonna just make it less picky. Okay, now back to where we were. I've started splitting our reference implementation in one module. The definition module contains the implementation in our handmade assembly, and so now I can compare the performance of the two implementations. So I'm going to bench. Let's start with an easy one. And so I'm always a bit lost when I mean, Criterion is nice, but it needs a bit of time to come back to it, to understand again how it works. So I'm going to use definition. So my crate is called, I don't even know, activations. Super. I'm going to import reference and reference for now. And I can use reference relu. and I should get first bench, cargo bench. While it's running, I'm setting up something I forgot. I'm setting up a SSH tunnel to the machine while it runs, so that we can hopefully see some graphs and stuff, because it does a HTML report. Okay. Just 1 minute. Sonostruct linalk activation. Starting my web server. Okay, and so if I look at yes, and so this is what we've coded, and here nope. So I don't have my criterion report yet. Okay, we'll see. So PS is picoseconds. That's good. It is working. So now I need to compare two implementation of the function. So comparing functions. So we have a slow and a fast. So what we want to compare is reference relu with definition relu, dot compute dot whatever, so I'm going to do a c dot benchmark group relu, and in this group they are comparing 2021. Yes. So in our case later we're going to use this for the size of the input, but for now we will just bench our two implementation. So one will be called reference, the other will be called definition or VM, and the first will run reference relu, and can actually, I think I can do it like that, but it's safer to do it, to use a black box to make sure. The black box is just a way to make sure that the compiler will not, the optimizer will not intercept our calls and optimize them away, because we are basically computing the same thing over and over again. So yes, for E in 1 for now, make it simple. E should be fine, and it needs it to be E32. I can do that. Nope. What? Let's look at the example again. It's calling iter, so it gets, yeah. Yeah, that's it. Then, so I have no x. I'm just calling one dot. Okay. Okay, so in the other iteration, I'm going to do I'm already there, so reference, so it's definition. So I need to call it first, so I don't want to bench the construction of the function, I don't want to bench the execution. D.compute black box of 1.0 f32. Okay, compute is private. Now it's public. Yes, I don't need this anymore. Let's see. So E for now is 1 because we only have one value, but ultimately it will iterate over several values, several size that we want to bench. Okay, we need to clean up a bit, because this won't help us being fast. Main is no longer needed. Debug. That one can stay. Running again. I think I know why I didn't get the HTML report. It's because they changed the way you need to invoke criterion. Before, it was all embedded into the executable, but now it's, if I remember correctly, now it's yeah, it's part of cargo. So it's a cargo subcommand. So the max is running at, so this is not super easy to interpret, about 1 nanosecond, and the VM is running at 16 nanoseconds. So the VM is 16 times slower than the reference implementation, which is not a big surprise. How to derive these for each function. So let's say that we will need, we can use, I mean, we could make this yes, okay, there. I want to look at the report first. Target, criterion, maybe it was there before, reports, index, review, okay. So, yeah, it's not super interesting, except we have 2 modes, which is a bit surprising. It's a bit suspect to have 2 modes like that. I can't really see why there would be 2 modes. Okay, well, I mean, there is kind of 2 modes here too. We have this little, but yeah, it's a bit weird. We'll see later. I can't explain it right now. I don't know. Let's try to iterate on the sizes. So one element, 32, 100, let's say 256. And how will this work? Well, for now, the implementations that we have are all working on one single value at a time. So it's as simple as doing, I need to prepare my input. So how do I do that? Okay, let's go back to Criterion documentation. To benchmarking with input. So this is my equivalent to what I'm doing. So yeah, this is super interesting because it gives us a nice output, like how many you can compute by seconds, which is much better for what we are trying to do. So this is just a display thing. You should choose if you want it to be displayed in bytes or in anything else. Maybe throughput elements, and I'm gonna use elements. Yes, VI is lost. Okay, and then yeah, so that's I need to define an input and and for that I think I need the other iter function. So .risk.criterion, and it's in iter batch. Yeah. Use this when the routine must consume its input. Yes, it can, but maybe I can just use, let's see the various different form of iter we have. We have iter batch ref. So this one will not consume the input. Okay, I'm gonna use this because input is actually, I mean, it's kind of consumed. Iter batched. I'm just not sure. Okay. Iter batched. Okay. And so iter batch setup. So the first routine will build, will take E as input. So E is a size, and I'm going to build a vector of 1.0 and of size E as your size. So that's my first routine, and then this guy will take my vector V as input, and it will do V for X in V X. Okay, it doesn't work. Expected 3 arguments. Yeah, I need to add something called the batch size. Batch size. And I'm going to use millions. No, not millions. Large input. Okay, so this guy is not at the right place. Okay, so what's wrong now? expected nothing found F32. Okay. What's wrong now? Cannot find value I in this scope. Yeah, it's now called size, which is a much better name. Size. Okay, and so the second one will be more or less identical, except that bit. I can cut and paste all of these up. I'm going to change that one, VM. And I'm going to change the inner function so that it does X cleaning up. Okay. So now it's iterating over the functions here, and I mean over the size and over the two implementations. So we have reference and VM as implementation, and we can see here VM process 41 million of elements per second, while the reference implementation goes, well, now it's only 3 to 4 times faster. Before it was like 16. I don't know why. Let's look. So when it's bigger, when we have a bigger array, we have 59. Yeah, so we are more or less in the ballpark. I mean, we have like 10 to 12 factor here. Here we have a 15 or so. 61 to 900. 61 to 900. Yeah, so we're back to a factor of 15 or 16 between the two implementations. Okay. I was expecting that. It's not a big surprise, and it should be over now. Yep. I'm going to commit this because I did a couple of changes. So please ignore this, and I'm going to add my benches directory. Benches first commit. Okay, so now I want to do the same for the dozen function that we have. We will define this for, and we will call either that or this. So it will look like, I will also need to change relu, so I want function name. So the name is string, and I will take a function that takes f and read f as a so let's call it reference. r. It will be a function of f32 to f32. Going to abbreviate this. And I need the, so for the other one, I will need the D. The D is definition, so I'm going to call it prog, and it's a program. That's how it's called in our bit of library. Okay, so now I'm gonna have for yeah. So now I can register all of my benches using a simpler syntax. So that's create C, name is relu, x done reference relu. I can even dispense with this. And D is definition relu. What's wrong now? Arguments are incorrect. No kidding. Yes, definition relu like this and like that. Okay, so I don't need this anymore. D is now prog. Okay. So let's try hard swish, for instance. And I'm going to look at exp2f. And also at sigmoid. Okay, so the bench will start to take some time to run. Plus, it's slower because of what? Because of probably me doing stuff while it's running. That's a problem when you run the bench on the same computer. I mean, on a computer which is busy doing other stuff, like running Rust analyzer and Rust compiler all the time. But still, I'm trying to figure out, was it expected to see these differences? Not too sure. Why do I get a warning here? I'm not sure. VI is not helping. I'm not using R. Oh, okay. Yes, so R here should be called like this. And I want to try trying to discard this ugly message warning that I have at every startup. of and it comes from, I guess, cargo/config. Yes, okay. It should be gone. So I'm going to run just sigmoid just to see. So one case is really not super interesting. So we still have a factor of 5. Okay, and the VM sigmoid is stable at like 13 million of computation seconds. The other is growing now. Once again, it's no surprises here. We'll do better. We'll improve on that a lot, hopefully. Okay. So what's next? So we have our bench, and they are dreadful, like we were expecting them to be. So now the next step is to start introducing some parallelism in the computation. So, for instance, the first thing we can do is commit this. So, what we've done here is we have the compute function that only takes one value at a time. But what we want to do is a compute function that will take 100 or 1,000 of value at a time and compute them in vectorized form. So we'll first do the interface part of it, and then we look at how we can actually run them in vectors. So I think the first thing to do is to accept a slice that we're going to mute in place. And we're going to do the same thing all over again, but I think it's not a good idea to... I mean, we could do it actually by iterating over and over and over. We can try this. So we know that, first of all, we remove D because we know that we only need 3 of them. So here, that's 3. So what I'm going to do is I'm going to say that we have A, B, C, which are the 3 registers. There will be 3 vectors of same size as X. So A will be a vector of, yep, A will be a vector of, will be a copy of X as a vector. B will be a vector of zeros in the same numbers. And C will be the same. So my three registers are I, B, and C. And actually, for A, I will not even do a copy. I will just use X directly, like that. So A mod B, A mod C. Okay. Initializing my constants. And then we can go and we can start these. So moving, we need to std slice copy, no, std mem copy, yes. What? No, that's not what I want. I want to copy. What if I do, actually, what if I do this? So expected, okay. I'm lost. Oh no, it's a very simple thing. Copy slice copy. So okie doke. I know I can do a for loop. I just want to. I don't want to write it. Okie doke. It's actually a mem copy that I want. Copy from slice. Okay. Yes, this is what I was looking for. Okay, much better. So that's one. So for this one, I need to copy constant everywhere. I guess the best way to do this is actually like this. For each x equals constant. Okay. Itermut for each okay. Next is recip. Recip is about of the same kind of thing. I have one more like this at the end. So this is floor. Next one is one more like this. So yes. X equals this X. Here we go. Then we have this one also easy because they will be of the same form, except instead of doing this, I can do plus x plus equal and constant of const, and that's my add. Sub mul min and max will have the same shape. Sub mul min and max. So sub minus mul times, and these two need a bit more work. X dot min and x dot max. Okay. Okay, so this one needs an asterisk. Okay. So now we have these guys who take two of them. So we're going to do regs 0 dot iter mut dot zip regs 1 dot for each x and y, and it's add, so x plus equals y. Yes, I can remove this. For each tuple, here we go. Okay, so I have one, add sub mul min max, add sub mul min and max. So same stuff, sub mul x dot min the y and x dot max the y of y. So French. Then this one again, same spirit, except it has a constant. So we need to do x equals x times y I'm doing FMA. I mean, it's not super clear here. FMA. Yep. So x plus constant that one we need to zip the three values together. So yeah, zipping more than two values with the Rust standard library is a bit cumbersome. But I mean, it's just once, so it's okay. The alternative is to put iteratools in the mix, because it has a nice zip function that can take any number of iterators to zip together. It's much nicer than this deep x2. And for each, so yeah, the problem is here, but with 3 it's still okay. So x, y, z, and if x positive, return y, else z. XYZ, what's wrong? So yeah, it's wrong because it's actually x with y, then z. Okay. What's wrong now? Yeah, there is one too many. Okay. Whoa. All right, so let's go back from the beginning. Cannot borrow. Ah. Yes. Okay, so the good news is, well, I mean, except for this one, for the move, but for all of them, we have fixed the registers are actually fixed. What I mean is, I mean, for instance, this one is always between A and B. So what I will do is let mut A equals X. This is just a matter of understanding what we are doing. So for now, I'm forgetting about this. And here it's A. So I need to replace reg 0 by A. like this. Rex1 is B. Rex2 is C. This one is A. This one is A. So now we have the tricky ones. So this one I will do will duplicate. Just duplicate. Aloka? Come on. Okay, so load to A, load to B, and load to C. C, B. What else? What's wrong here? Okay, so that's just a bit of... Yeah, I need to do this instead. Okay. What's next? Here, same problem. So this one is a bit tricky. So I'm going to do it very naively. I mean, I can actually borrow both of them, so I can swap. So b.itermut .zip c.itermut .for each. Actually, no, because take a tuple. B and C. Okay, that guy needs an ampersand. And we are back to the move. So, I mean, if I want to do all of the cases, I need 6 of them, which is not great. But I think there is a way to do a multiple borrow in a slice. With like something like split slice. So I'm looking for a way to... Whoa, this is interesting. New. Yeah, portable SIMD. Okay. Portable SIMD is... I mean, there's a lot of things to say about portable SIMD. I would love to be able to use these APIs, but it's unclear if there is actually some development going on them. Anyway, let's not get rid of ourselves. Copy from cell, copy within. I'm looking for a thing that allow to... Yes. Exactly. Nightly. Ah, shame. All of them nightly. Okay, it's fine because there is a, I think it's split nightly, split array mute nightly, split at mute. Ah, I knew there was one. So this one will give me two mutable slice. Okay, and I divide 2 at an index. Okay, so first register will be let A, B, C. A bit so complicated. Yes, it is. So let regs equals ABC. Okay. So I need to split at the position of the bigger of the two. So let's split, let's left, right. Okay, it's a bit stupid, but let's start with the case where DST is left. So I'm splitting, I will split my slice into two slices at the position of SRC. So regs.split at SRC. So from there, in left, I'm starting at 0. So SRC is left of SRC. And destination is right of 0 because I split it at it's all wrong. So I split at SRC. So the source is right of 0 and the destination is left SRC. And now I can do d.copy from slice OS. As you size with a star maybe. Yes. Know what? Okay. Okay. And the other case. So now DST is bigger, so I'm splitting at DST. Destination is the first element on the right, and the source is SRC. Is it right? Yes. Okay. So that's for the move. Just have to make it work now. So A. Why did it move the value? right. I don't care. So now the three of them are vectors. It should make a lot of things a bit easier. Yes. That's a lot of mute. I want the slices. Okay. This one doesn't have to be mute actually. Cannot borrow left as mutable as it is behind ampersand. Split at mute. What now? I need to be mute. Okay. This one is useless. Alright, so same here. I'm splitting at mute. And emute star star. Emute, not mute, star star. Other way around. Okay. Next. Yes, there is something is supposed to be wrong. Load. Load, yes, okay. It's not smart enough to detect that. I've managed all the loads. Okay. So we're going to need to test all of this. And to do that, I'm starting to be a bit bored about repeating over and over and over every single test. Going to start moving stuff into modules because the file is too big for its own good. So that's reference pif path. Pif path. So okay. So now what I could do, but I don't want to do that. I could replace the compute method by something that creates a slice and call compute and call the same function compute slice. I don't want to do it because I want to keep the bench. I want to keep the availability to bench both functions. So no, I'm not going to do this. I'm going to because what I need to do is I need to duplicate this to do something like that actually. Compute slice. And this is yeah, it's not even like that. I need to build a slice, call the function on a mutable, and then extract the value. So how to do it without repeating all of these? I'm not 100% sure the right way to go here. The thing is, these are very close to be macros, and I mean, these guys have extra values, but that should be okay. Let's try a macro. So I'm going to take name of the function, prop active. I'm going to take. So I will have to build some name like this because actually I'm in test, so that should be okay. So I need the name, which is an identifier. I will need the params, so that's x, alpha, and beta. Or it's just alpha and beta actually, because x is special. So the params will be, so they are all F32, so I can just take identifiers. And I need to generate this, so that will look like I'm not sure if it's going to work because I'm doing macros. I mean, it will have to expand, and we'll see. I'm not sure how prop test bang will interact with the rest, but we'll see. So that's going, and what I want to do is I want to be able to comment that guy and do prop activation, relu, and so prop activation relu, and that's it actually, because it doesn't have extra parameters. So is it testing? No, it's red. So I said that I was expecting parameters. As identifiers, and I have none, which should be fine. and then I'm closing it. So I'm not sure. Why? Okay, let's take it step by step. First, let's try to make that stuff work. No. Yeah, so this guy is not happy. But it's okay, because maybe I can just put it inside instead of putting it around. Yes, it's testing. So now I need to add the extra parameters. So params will be, I'm not sure to deal with this. I can do that. It will be nice, I think. So param that yes will be also an ident. And this can repeat. So review would be this, and affine would be affine would be alpha and beta. So yeah, I need here, yeah. So param de column in any F32 and here same, so param it would be nice if it works. But I'm starting to doubt param. So in any F32, okay. And now this method takes one argument, but 3 arguments were supplied. Yes, because the params come here actually. This is why I splitted them in the first place. Yay! Okay. That's pretty good. So leaky relu takes alpha. Threshold takes alpha. Subsign takes nothing. Subsign. Is it subsign? No, it's offsign. Even better. Hard swish. Sigmoid. my old friend. And finally, x2f. Cannot find soft sign. What did I do? Probably something a bit stupid. Where are we? Soft subsign. Okay. Just to make sure. So now that I know I can do this, and I need to switch this to use prop insert close enough A and B. It's a good sign. It means that the rest is working. Yes, we can see these debugs. We still have, we have some serious issue here actually. Leaky relu is broken. Leaky is broken. And affine is broken too. Okay. Yes, but it's not a bug actually. I mean, it's a bug in the test, I think, because it's complaining because of env not being equal to env. So if A and B are infinite, then the comparison is broken. So A is infinite and A is and B is infinite and A dot signum equals B, because that's I can check. I can check that they're infinite of the same sign. Okay. Nope. Not okay. Now everything is broken. Yes, because it's either this or the rest. Okay, back to normal. So now now we can try to test our slice implementation. So the thing is, I will need because I need to generate function names for the test. I mean, either I use the function names, but I can do something like that. So scalar. So if I do this, all these tests will be under scalar, which means if I want to generate more, I can I can. I just have to put them on a different module. Prop test, yeah. So yeah, I need to move a couple of things. So super doesn't work anymore. I will use create instead. As for close enough, I need to import it. Okay, and we're back. So now I can do the same with the vector implementations. And so now I need to make a slice. And I need to call here compute slice. And I cannot compare right away, so I need to do this first. Here we go. And I can use slice of 0 here and compare this to the reference implementation. And this should give me, if you can make it work, we should have all the tests. Not passing. Okay. We'll start with relu because it's the easiest one. So no, it's not good at all. Why? Because I think because I have copied the value to A at some point because I got a bit lazy. So let's try to do it again like that. So I'm saying A, I don't need A. I'm going to use X. We're back to this one. But that's okay. So now what's wrong with A? Yeah, A is now X. Good. Burrow. Okay, so now the burrow checker is going to be. Burrow checker is going to be annoying because here I'm moving the mutable. So what if I? What if I drop regs here? No, same. Yeah, so that's a problem because I cannot copy a mutable slice, even if it would be okay in this occurrence. Can I clone it? No, I don't think so. No, that would be wrong. Okay, let's go back to what it was. And okay, access to vec. But at the end, I need to copy access.copy from slice A to put the right value in the right place. Okay, passing, and the other, not quite. Okay, leaky is not passing. Leaky is an easy one. What does it have? What does leaky have? Leaky have move, mule, move, and if positive then. So let's look at if positive then first. X positive, Y elsin, that looks good. It has mul by const, looks good. And it has moves. So maybe I did something wrong with the move. Actually, except yeah, the other two also have moves. And we also have another indices. Another hint is index out of bound. So that's clearly lines 58. So that's clearly there is something wrong here. So I'm splitting at SRC. So that's DST. Okay. Yes, everything is good. So now we have our vector implementation, and we can look at the bench again. No, we can't. We need to implement it. So I'm going to call, yes, it's very simple, compute slice. Here we go. And whoa. Why? I mean, it's these values are so small that it's super hard to get an exact, to get a precise measurement of the performance on this kind of values. So 32 is more interesting and it's more stable. So let's see how VMVec performs. Suspense 220, so it's somewhere in between. Reference was 600 millions of elements per second. the initial VM was 60, and with vectorization is 220. And let's see if it stays like that with other sizes. No. Now the VM vectorize is outperforming the other two. We get over 1 giga element per second. That's it's getting better. That's good news. Yes. Last size. Hoping it to be about the same. Yeah, 2 billion. Oh, that's good. I would like to move to sigmoid. I think I'm going to stop right there for tonight because I'm tired and and nobody's watching anyway. So it's a good 2-hour session already. Let's just see how hard switch is performing with bigger slices. In the meantime, I'm going to commit so hard switch is not, I mean, will 276, yeah, at 276 we are close to the reference speed, and I think that after that we're getting even better. So VMVec is 1.2. It's actually pretty good because I think the best we could hope for with this CPU is 50 billions multiplication per second, and RSwish requires at least 2 of them, if I remember correctly. Oops. RSwish has, okay, just 2 of them, so it's less than I thought, but still, it's only, I mean, it's only wasting. I mean, it's 2 billion multiplication per second, and this the CPU of this computer, 1 core could handle 50. So it's not ridiculously lower. It's just 20 times not as good as it could be if we just take into account the multiplication. I thought it wouldn't be that good. I thought it would be worse. Exponentiation. So the reference here is 256. 200 million of operations. And yes, our simple vector code is already faster. So that's good because we're not done. This is only this is only an intermediary step, because here we are just relying on whatever the compiler can do to vectorize the code, and I'm not even sure that it's trying that hard. So if we start actually writing this in assembly, we should be much faster. So 200 for reference on exponentiation, and VM is super bad at 12, but once in vector form, 259, so better than reference. That's good. Let's have a look at sigmoid, and then we'll call it a night. So VM vec is worse than VM when there is only one element. Big surprise again. 32 is not that interesting. 226. (11 or 12 for the VM, and in vector form. 114. Okay. 256 is usually the one where I think where the vector VM is better than reference. So let's see for sigmoid. Sigmoid is the only one with a division in it. Not the only one, but okay, yes, we are. I mean, the VM vectorized is better than reference with 256, and 256. It's not a big number in your networks, so it's a pretty good sign that we can do something nice. $450 compared to 260. Last comparison. $260 vs 12 vs. Okay, not great. I mean, it was better, but I did some stuff. Okay, so as I was saying, this is all for tonight. And next week we'll look more into maybe we'll look at what the compiler did. But if you want to do that, I will move away from Intel and go to ARM. Because it's the assembly is nicer, and then we will start working on the assembly part. All right, thanks for watching. Not on live because I think there was just nobody tonight, but on YouTube. Bye guys.